We need to find all integer x values where there is an integer y that makes x times y equal to 15. This means x must be a divisor of 15, and the integer divisors of 15 are plus minus 1, 3, 5, and 15. So it's the final set. We have two sets. X is from -1, 0, and 1, and y is from the set 0, 1, and 2. So we add every x with every y. -1, 0, 1, 0, 1, 2, 1, 2, and 3. So the final unit numbers are -1, 0, 1, 2, and 3. We need to determine whether each statement is true or false. So first is true, because the empty set is always a subset of itself. B is true, empty set is a subset of any set, including this one. C is false, the empty set has no elements, so it doesn't contain itself. D is true, because this set has one element, which is empty set. E is true, this set has members, so this set had members, no sets, so this set is not inside. F is false, same as before, this set is not an element here. G is also false, because only numbers and set of 1 and 2 are in 1 and 2 itself. H is true, the set of 1 and 2 is explicitly set here as an element. I is false, because the set of 1 and 2 is not an element of 1 and 2, so not a subset.
So now let's start solving the second task from the second section, and here we have two sets, S and T, and in the first task we should try to find their intersection. So as we know, intersection is a set of elements that are contained in both given sets, in our case S and T. That's why we should write square root of 2 and 25. As we see, they're both contained in S set and the T set. Then we should write the union of these two sets. Union is a set that contains all elements from the first set and the second set. So firstly we write all elements from the set S, 2, 5, square root of 2, 25, e, and 5 over 2. Then we look at the set T, write 4, 25 and the square root of 2 we skip, as we have already written them. And also we write 6 and 3 over 2. The next task is to find the Cartesian product of T set and the intersection of S and T. As we have already found it, I just rewrite it. And now we should combine pairs of elements of T and elements of this intersection. And so, for example, we take 4 and make pair with square root of 2 and with 25, and so on with other elements. In the B task, we should find the union and intersection of our given sets with the set of all integers, Z. So firstly, for our convenience, I decided to write numbers from original sets that are not integers. So in case of S, it's the square root of 2, pi, and 5 over 2. And then we just see the sequence of all integers. It's 0, 1, minus 1, 2, minus 2, and so on till infinity. To find the intersection of Z and S, we should just write all integers from the set S. It's 2, 5, 25. The same thing we do with the set T. In C task, we should find the intersection of set of all integers with the union of sets C and T. This part I just rewrite from the A task. And now we can easily find all integers from this set. It's 2, 5, 25, 4, and 6. In the next part we should find the union of intersection of Z and S and Z and T. So again, I just rewrite it from the previous task, as we have already solved it. And here we can see that we have same numbers, 2, 5, 25, 4, 6, and here the same elements. That's why we can say that this expression is equivalent to this expression due to the distributivity law. And the same situation we can also see in the D part, because here we do the same actions and finally have the same answers in Z union with intersection of S and T, and the intersection of Z union with S and Z union with T. So in the first task, we are given a set A containing 6 pairs of elements, A and B, and in A part, we should write a set of some of the elements A and B, where all pairs are contained in set A. So basically, we just do -1 plus 2 is 1, 4 plus 5 is 9, 0 plus 0 is 0, 6 minus 5 is 1, but we already have this element, so I won't write it for a second time. 5 plus 1 is 6, and 4 plus 3 is 7. In the B part, we should write only A elements, where A is more than 0, and again, these pairs are contained in set A. So, as you can see, we have only 4 elements, 4, 6, 5, and 4 that are more than 0, and again, we can see that 4 is written 2 times, but we can write it only once in our final answer. And in C task, we should write B elements, where B is a square of integer k, some integer k. So from given numbers, only 0 and 1 can be considered as a square numbers of some integer. That's why our final set contains only 2 elements.
Section 4, exercise 9, A part. In this problem, we define a relation on the set of integers using the condition that A relation B if only if 3A plus B is a multiple of 4. So to prove that relation, firstly we have to check the first property is reflexivity. We need to show that some A integers, A is related to itself. So substituting B to A, we get 3A plus A equal to 4A, which is always multiple of 4A. So for the next property, symmetry, for the symmetry, if A relation to B, then 3A plus B equal to 4K for any integer, we express B in terms of A and B in terms of B, and substitute B into the next expression, and after simplifying the result we can see that it's a multiple of 4, so we can say that this relation is symmetry. So for the next property, transitivity, for transitivity of A relation to B and B relation to C, we had the 2 given equation, first one and the second one. So after adding and simplifying, we can see the result is a multiple of 4, so we can see that the relation is transitive. Since we proved reflexivity, symmetry, and transitivity relation, so we can say that this relation is equivalence relation. B part of exercise 9, we have to find the equivalence class of 0. The equivalence class of 0 consists of all integers and satisfies this expression. To find the equivalence class of 0, we need to solve 3x plus 0 by the testing values. We can choose any numbers. For example, if we pick the 0, after substituting, we get the 0. This number is a multiple of 4. So the next one, we pick the 4, and after that, we get the result 12. It's a multiple of 4 also. And the next one, if we take the negative 4, the result will be negative 12. It's also multiple of 4. And if we take the 1, and after substituting, we get 3, and this is another multiple of 4. So by picking this number, we can see the pattern. It's 4z. Z is any integer number, and the equivalence class of 0 consists of all z numbers, or we can determine it by this pattern. So the C part of 9th exercise, we also have to find the equivalence class of 2, which is satisfied this expression, and it's multiple of 4. And we also use the testing values method. We pick the 2 and substitute it into the x, and after we get the 8, and this number is a multiple of 4. We after pick the 6 number, its result will be 20. It's also multiple of 4. And after negative 2, we also get the minus 4, and it's also multiple of 4. But if we choose 3 number, the result will be 11, and it's another multiple. So by this number which we picked, we can see also the pattern, which is 4 multiplying to z. Z is any integer number, and plus 2. And by this we can see the equivalence class of 2, which consists of that set of number. On the D part, we have to get the quotient set. The quotient set consists of all distinct equivalence classes, and from our previous calculation we found the zeros equivalence class and equivalence class of 2, and in this part we have to find another equivalence classes. It's the first and third, and also by the previous method, by the testing values, we find out this pattern for the equivalence class of 1 it's 4z plus 1, and for the equivalence class of 3 it's 4z plus 3. So the quotient set consists of all the set of equivalence classes. Section 4, exercise 11. In this exercise we have to define the equivalence relation of that expression that a and b belongs to z without 0, and also satisfy this condition that a multiplied b is greater than 0. So first we have to check the reflexive property. We need to show that for any integer a is related to itself, since in any integer multiplying to itself it's a squared. So we can say that any integer is multiplying to itself is a positive number. So we can say that this relation is reflexive. So the next property is symmetry property. We can see that since multiplication is commutative, so a multiplying b is also the same as b multiplying to a. So we can say that this relation is symmetric. And for the transitive property, if a relation b and b relation c implies a relation to c, we can show that if a multiplying b is greater than 0 and b multiplying c is greater than 0, so we can assume that also the a multiplying to c is greater than 0. Therefore, the relation is in transitive and also equivalence relation. B part of 11th exercise, we have to find the equivalence class of 5 and negative 5. Since the equivalence class of 5 consists of all integers related to 5, meaning that a multiplying to 5 has to be greater than 0. And after that we can consider that any positive number multiplying to 5 is always greater than 0. So the equivalence class of 5 is all the positive integers number and contains all that set. And for the negative 5, the equivalence class contains all the negative part of the integer. Since a to be greater than 0, we have to multiply such number which just contains a negative sign, and after multiplying to the negative 5 we will get the result of which is greater than 0. So the equivalence class of negative 5 is also negative integer set. For the C part of 11th exercise, we have to find the partition of Z, difference of set of 0. Since every number is either positive or negative, this equivalence relation splits into two groups, one for all positive numbers and one of all negative numbers. So this is the answer.
Now let's continue solving the fifth section, and we'll start with the fifth task. In A and B parts, we should draw the Hayes diagrams for the given sets. So in the A part, we have a sign less or equal than. That's why we will just draw a simple vertical line containing all elements in such order that on the top we have the biggest element and on the bottom we have the last element. That's 1. The B part is a bit more difficult, as here we have the sign of a subset. That's why we should draw the Hayes diagram in such way that on the top we have the set that contains the biggest amount of elements, and on the bottom we have the set that contains the less amount of elements. So here, for example, A, B, and C, the set containing these elements is a subset of A, B, C, and D. So sixth task is connected with the fifth, as here we should find maximal, minimal, and maximum and minimum. You should remember that maximal and maximum is not the same, as maximum element is bigger than every other element in the set, while a maximal element is one that isn't less than any other element. So in case of A, the maximal and maximum elements will be the same, it's 6, and minimal and minimum element is 1. In B part, maximal and maximum elements again is the same, it's the set containing A, B, C, and D, but we have different situation in minimal and minimum. Minimal elements are the sets containing A and the set containing C and D. And in this case, we don't have a minimum element because we don't have a set that will be a subset of all other elements. So for example, if we had an empty set like this, it would be connected with the set A and the sets containing C and D, and it would be the minimum element. But as we don't have it in our task, we don't have a minimum. Let's solve the first task, and we are given 3 sets, A, B, and C, and for your convenience, I wrote all elements that are contained in A and B sets, and we need to find elements in this equation. So the first symbol is a symmetric difference, and it means that we should write all elements that are in A or B, but not in both. So in our case, we have only 3 elements. 1 and 2 are contained in A but not in B, and 7 is contained in B but not in A. And then we should find set difference between 1 to 7 and set C, which contains 2 and 3. And the final answer is 1, 7.
Homework 2, task 2, discrete mathematics. Let's get started. A equals x contains z, and we have an equation -1, x more or equal -1, and x less or equal to. Let's find a. This equation means a includes integers from -1 to 2, so a equals -1, 0, 1, 2. Let's find b. It's definite at b equals 2x minus 3, and x includes a. We substitute each element of a into the expression. We substitute and get some values that contains b. So b equals -5, -3, -1, 1. Now set c is given by this equation. We substitute b, and a includes b. Let's get substitute and catch some sets. Let's start task B. We have 2 sets of elements A and B, and V intersection of A and B. The common elements are -1 and 1, so intersection B is -1, 1. Let's go with task B. We find intersection. Теперь let's get Cartesian products. It means we take intersections elements sets, and we combine every element of other sets. In our case, it's B, and we get all 8 different subsets. -1, -1 is combined with themselves. Let's get start C. B is not C, which means the elements of B is not C. Just it's equals -5, -3, -1, 1. It's because C contains only fractions and B contains only integers. That's because some elements are in C. And let's get D, task D, A and A symmetric difference C is equal -1, 0, 1, 2, -5/4, -3/4, -1/4, 1/4. Why we get it? It's because C again contains only fractions, and B only integers. We have symmetric difference. It means we contain only different. When we compare two subsets, we combine only the values that's not in other sets. That's because each element in one row from A and C.
Review part of chapter 2, exercise 13. In this exercise we have to determine whether a relation is reflexive, symmetric, antisymmetric, transitive, or if it's equivalence relation or partial order on A. So in the A part, we can see that A is a set of all natural number for which A and B belongs to set of A, and condition that is A less or equal to 2B. So the first property is reflexivity. We can see that a relation is reflexive if each element is related to itself. Here, since A less than 2A is always true, so the relation is reflexive. The next property is symmetry. To prove that property, we can use the example. Take for the A1 is 2 and for the B variable 6. And after substituting, we can see that 2 is less or equal than 12, but 6 is not less or equal than 4, so it's false, and we can say that relation is not symmetric. The next property is antisymmetric. This means that if both A relation B and B relation A hold, then A must be equal to B. So, but if we take A equal to A2 and B equal to 3, and after substituting into our equation, we can see that that A part is not equal to B part, so the relation is not antisymmetric. And for the next part is transitivity. To check the transitivity property, we also can pick any number for our variables. Is A equal to 3, B equal to 2, C equal to 1. And then after making the relation, we can see that A relation B is true, B relation C is true, but A relation C is not true. So we can say that the relation is not transitive.
In 15th task, we should find the relation R on Z, and firstly we would start with finding whether R is a reflexive relation or not. So for any A which lies in Z, 4A plus A equals to 5A, and as we all know, 5A is always a multiple of 5, that's why this relation R is always reflexive. The next point is finding whether this relation is symmetric or not. So we assume as a fact that 4A plus B is a multiple of 5, and then we need to check whether 4B plus 5A is also a multiple of 5. So we need to rewrite this expression in the form 5 multiply B plus A minus B plus 4A. We know that B plus 4A is a multiple of 5. And B plus A multiplied by 5 is also a multiple of 5. That's why all this expression is also a multiple of 5, and this relation is symmetric. Both these equations are multiple of 5, and if we sum them up, their sum will be also a multiple of 5. Then we take this sum and subtract 5b. If we subtract numbers that is also a multiple of 5, our final result will be also a multiple of 5. That's why our relation is transitive. So we have that relation is reflexive, symmetric, and transitive. That's why R is that R defines an equivalence relation on Z.
Set A equals 1, 2, 4, 6, and 8. We define relation as A less than or equal to B if and only if B divided by A is an integer. In other words, A divided B. And we need to check three properties. Reflexive, every number divides itself. So for any numbers A divides A, the relation is reflexive. Second is antisymmetric. If A divides B and B divides A, then A must be equal to B. So the relation is antisymmetric. Transitive. If A divides B and B divides C, then A divides C. So the relation is transitive. Let's find which numbers divide which in the set A. 1 divided 2, 4, 6, and 8. 2 divided 2, 6, 8. 4 divides 8. And 6 and 8 divides only themselves. We draw the Hassel diagram, and 1 is below 2, 2 is below 4 and 6, 4 is below 8. Minimum element is 1 because it divides all others. Maximum element is not because there is no single number that is divisible by all. Minimal element is 1. There is only one with nothing below it. And the maximal elements is 6 and 8 because no numbers in the set are above them. D is not a total order because not every pair of elements can be compared. For example, 6 and 8. 6 doesn't divide 8 and 8 doesn't divide 6.